In this video, I'm going to walk through a roll feeder sizing example using the Sigma Select software. Hi, I am Micah Studeman. Here's a quick preview. We're going to walk through sizing a draw roller for a bag sealing machine. The draw roller specification and motion profiles have been defined and can be loaded into the Sigma Select software to find the best motor for this application. Now let's take a look at this in a little more detail. At this point, I assume that you have watched the following videos that introduce you to the sizing concepts and software. Here's a visual representation of a simple bag sealing machine. The machine consists of a sealer actuator and two draw rollers, which are driven through a belt and pulley system. The bags come down the line, and the sealer comes down to seal and perforate the bottom of the bag. The plastic is then indexed to seal the next bag. So what size of motor is required for the draw roller? The load characteristics and motion profile are both important. The following specifications have been obtained for sizing the draw roller. The vertical sealing motion is not being sized in this video. The draw rollers consist of an aluminum cylinder that has a rubber coating to grip the bags. The motor drives the rollers through an aluminum pulley system that has a 3:2 gear ratio. The machine is required to make at least 200 bags per minute. So how many seconds per bag is required? That's 60 seconds for 200 bags, which equals 300 milliseconds per bag. The 20.6-inch move therefore must be completed in 200 milliseconds to allow for a 100 millisecond pause to perforate and seal the bag. For this application, keeping the XL and decel time higher is preferred. This prevents deforming the bag material. The mechanical design of the machine limits the speed to 200 inches per second. Let's start sizing the motor by opening the Sigma Select software. For this example, I will be using version 1.0.8.3. To start, I have already filled out the user information section. In the Load Editor tab, we can start filling in some required information. First of all, what mechanism are we trying to size the motor for? In this case, it will be for the draw roller portion of the machine. So I will select the roll feeder icon from the left side. Let's look into some of the load info. First in this section is the press force and tension force values. What should be entered here? Looking at the mechanism and the spec sheet, we have 5 pounds of force coming from a spring pressing the top roller down into the material. But press force includes all of the forces that are pressing into the material. This includes the weight of the top roller. That mass will be calculated in the driving roller inertia calculator. For right now, let's set the press force to 5 pounds, and the roller weight will be added later. The tension force in the spec sheet is listed as 10 pounds. This force can be either positive or negative. Tension at the input of the draw roller would be modeled as a negative tension force. In this situation, the tension force is positive because something downstream is keeping the tension on the draw roller's output. So let's set the tension force to a positive 10-pound force. For completeness, you should model the force due to friction between the bag material and the machine surface. In the friction calculator, the closest materials are PTFE on steel. Let's use this estimation as the coefficient of friction. Any additional friction force can be entered here. Now that the load is defined, the next step is to fill in the mechanism properties, which are defined by the mechanism type that was selected earlier. The driving roller diameter can be found in the spec sheet and is 80 millimeters. Now for the draw roller's inertia, if you remember from the servo sizing basic concept video, the moment of inertia is a measurement of how difficult it is to change the rotating velocity of the object. In this scenario, we're looking for the inertia of both of the draw rollers. The specification does not list the inertia directly, but we do know the material and the dimensions. This can be used in the inertia calculator. The inertia calculator takes a user-defined model of the draw roller and calculates the inertia of the defined model. In this case, there are two parts of the draw roller that need to be modeled: the inner aluminum roller and the rubber coating over the aluminum roller. I'll start with the inner aluminum roller. I'll set the label to roller and set the type to cylinder. There's only one driving roller, so the quantity will be 1. The ratio should be 1 because the belt pulley system ratio will be handled in a different section. Looking at the diagram, the roller needs to be modeled in the vertical orientation. From the spec, the length is 610 millimeters, so the height is 610 millimeters. The inner diameter of the roller is 0, and the outer is 80 millimeters minus the 2 millimeters of rubber coating. So I will put 76 millimeters for the outer diameter. The material will be aluminum. The rubber coating can now be modeled. I'll set the label to coating, and the quantity and ratio will be 1. From the spec sheet, the length is 610 millimeters, and the inner diameter should equal 76 millimeters, which is the outer diameter of the aluminum roller. The outer diameter of the rubber will be 80 millimeters because that is the overall diameter of the roller. The density for the rubber was given in the spec sheet and should be entered as a user-specified material. The inertia for the driving draw roller has been found. The mass of the roller and coating has been calculated, so it can be added to the press force in the load section. This comes out to roughly 22.4 pound force. Going back, the driving and driven rollers are the exact same, so the inertia can be copied from the driving roller inertia into the driven roller inertia. The efficiency of the draw roller depends on how much friction is within the roller mechanism itself. The rollers use ball bearings which have a common efficiency of roughly 90%. So let's set the efficiency to 90% or 0.9. The draw rollers are connected to the motor via a 3-to-2 pulley system. To fill in the transmission data, let's select the calculator icon. Multiple transmission components can be added if the system requires it. In the case of a draw roller, there's only the one pulley component. So let's set component 1 to pulley and name it pulley 1. Looking at the velocity ratio, this is where the gear ratio will be used from the spec sheet. The motor side will rotate 3 times to produce 2 rotations on the load side. This creates a gear ratio of 1.5. The pulleys and belt have an inertia ratio associated with them, so that can be calculated in the inertia calculator tool. From the spec sheet, we can add the input pulley information and the output pulley information. When adding the belt inertia, it is common practice to add all of the belt inertia to the input pulley inertia. According to the spec sheet, the belt weighs about 1 pound. So, to add the belt, we need to add it as a freeform object. And then set the weight to 1 pound. And it is offset from the center of the pulley, so we need to set that to 25 millimeters. One thing that is different here is that the gear ratio needs to be added into the output pulley's ratio. So let's set that to 0.66, because for every 1 rotation of the motor, the output pulley will rotate 2/3 of a rotation. A lower ratio decreases the reflected inertia. The inertia ratio for the pulleys has now been found. The transmission section is now finished. Let's move on to the profile editor. Now we need to move the information from the move profile, shown earlier, into the profile editor. To make sure that the correct units are used, I need to set the unit options to inches, seconds, and newtons. The first section is a trapezoidal move that occurs over 0.2 seconds. The distance should be set to 20.6 inches, and the speed should be set to 200 inches per second. This provides the slowest XL and decel values without pushing the speed higher than 200 inches per second. The second section is a dwell for 0.1 seconds, so that the sealer has time to seal and perforate the bag opening. Now the motion profile is finished, and a motor can be selected from the Motor Results tab. When selecting a motor, the following 4 key sizing factors need to be taken into account: inertia ratio, speed, max torque at speed, and RMS torque at speed. For this application, let's use a 200 volt Sigma 7 motor. Looking at the list, I want to find a motor that fulfills all 4 of the key sizing factors. But a rule of thumb to use when sizing is to make sure that the rated and peak torque factor of safety values are around 1.25 or higher. This allows a buffer if the customer specifications are a little off. The S7A15A-VL090-03 motor fulfills both the rated torque and peak torque factor of safety requirements by being close to or greater than 1.25. The SGM7G-44A non-gear motor also looks like it fulfills the 4 key sizing factors. Let's select both motors for right now. In the motor detail screen, I will look at the SGM7G-44A motor first. Looking at the speed torque graph, the RMS torque value lies in the continuous region, and the peak torque lies in the intermittent region. This satisfies 3 out of the 4 key sizing factors. Looking at the motor detail area, the inertia ratio falls underneath the allowed inertia ratio of the servo motor, so that satisfies the last key factor. Looking at the S7A 15A-VL090-03 motor, it appears that the required peak torque is really close to the intermittent torque limit. This appears to be a limiting factor for this motor. Let's select the next larger gear motor, which is the S7A 20A-090-03 motor. Looking at the speed torque graph, it appears that the peak torque is further away from the intermittent torque limit. So this motor should work. So, which motor should be used for this application? Looking at the motor sizes, the SGM7G motor is a 4.4 kilowatt motor, compared to the S7A 20A gear motor, which is a 2 kilowatt motor. Taking a quick look at the Regeneration tab, the SGM7G motor requires the use of an external regen resistor, where the S7A 20A motor does not need an external regen resistor. So in this case, the S7A 20A motor seems to be a good choice for this application. The sizing is now complete, and a sizing report can be created. The report contains all of the information that was used to size the motor, along with the motor specs of the selected motor. The S7A 20A-VL090-03 motor will work for running the draw rollers for the bag sealing machine. This concludes the draw roller sizing application. For more information on Sigma Select and motor sizing, visit Yaskawa.com.